lapel.
Learning her principles of biochemistry. Chapter 1: The Foundations of Biochemistry. Physical Foundations, Part 1. Living organisms exist in a dynamic steady state, never at equilibrium with their surroundings. Hey everyone, welcome to our video about living organisms and their dynamic steady state. Today, we're going to explore the concept of how living organisms are never at equilibrium with their surroundings. So, what does it mean for a living organism to be in a dynamic steady state? Well, it's all about maintaining a balance while constantly changing. Think of it like walking on a tightrope. You're constantly adjusting your balance to stay upright, but you're never completely still. The same goes for living organisms, they're always adjusting and adapting to their environment to stay alive. Now, let's break down some key terms. When we talk about a dynamic steady state, we're referring to a situation where the composition of a system remains relatively constant over time, even though continuous changes are happening within the system. This is different from being at equilibrium, where no net changes are occurring within the system. In living organisms, this dynamic steady state is maintained through various processes such as energy production, metabolism, and cellular functions. These processes ensure that the organism's internal environment remains stable, even as external conditions may change. One important thing to note is that living organisms are never truly at equilibrium with their surroundings. This means that they are always actively responding to changes in their environment, whether it's temperature, nutrient availability, or other factors. This constant adaptation is what allows living organisms to survive and thrive in a wide range of conditions. So, in conclusion, living organisms exist in a dynamic steady state, never at equilibrium with their surroundings. This dynamic nature allows them to constantly adapt and respond to changes in their environment, ensuring their survival and success. Organisms transform energy and matter from their surroundings. Have you ever wondered how living organisms transform energy and matter from their surroundings to sustain life? Living organisms are like tiny factories, constantly taking in raw materials and converting them into energy and building blocks for growth and maintenance. Let's break it down. For chemical reactions occurring in solution, we can define a system as all the constituent reactants and products, the solvent that contains them, and the immediate atmosphere. Organisms obtain energy from their surroundings in two ways: they take up chemical fuels from the environment and extract energy by oxidizing them, or they absorb energy from sunlight. The key descriptors of entropy are randomness and disorder, manifested in different ways. Entropy is a central concept in biochemistry. Life requires continual maintenance of order in the face of nature's tendency to increase randomness. As metabolic energy is spent to do cellular work, the randomness of the system plus surroundings increases as the potential energy of complex nutrient molecules decreases. Virtually all energy transductions in cells can be traced to the flow of electrons from one molecule to another, in a downhill flow from higher to lower electrochemical potential. Creating and maintaining order requires work and energy. Let's start with the idea of entropy. Entropy is a measure of randomness or disorder in a system. When a chemical reaction occurs, it can increase the randomness of molecules, leading to an increase in entropy. Now, the first law of thermodynamics tells us that energy is conserved in any physical or chemical change. This means that while energy is used by a system, it is not used up, rather, it is converted from one form into another. Two key players in cellular metabolism are ATP and NADPH. ATP acts as the energy currency of the cell, while NADPH carries electrons in a wide variety of reduction reactions in biosynthesis. Enzymes play a crucial role in metabolism by catalyzing chemical reactions. They lower the activation energy required for a reaction to occur, making it easier for the reaction to proceed at a faster rate. The overall network of enzyme-catalyzed pathways, both catabolic and anabolic, constitutes cellular metabolism. These pathways are interconnected and regulated to achieve balance and economy in the cell. So, there you have it. Creating and maintaining order in living organisms is a complex, energy-driven process that relies on the principles of thermodynamics and biochemistry. Thanks for watching, and stay curious. Box 1 to 3 Entropy, things fall apart. So, what exactly is entropy? Well, entropy refers to the randomness or disorder of the components of a chemical system. It's a central concept in biochemistry, and it's all about how life requires continual maintenance of order in the face of nature's tendency to increase randomness. Now, let's take a closer look at the three simple examples presented in box 1 to 3 to illustrate the nature of entropy. First, we have the tea kettle and the randomization of heat. This example helps us understand how heat energy becomes completely randomized throughout a system, leading to an increase in entropy. Next, we have the oxidation of glucose, which is a state not only of energy but also of matter. This example shows us how the oxidation of glucose results in an increase in the number of molecules, leading to an increase in entropy. Finally, we have an intriguing connection between information and entropy. The passage from Shakespeare's Julius Caesar is used to demonstrate how a non-random arrangement of letters contains a wealth of information, while a completely random arrangement contains little to no information but is rich in entropy. Now, let's talk about the implications of these examples in the context of living organisms and the concept of a steady state that is far from equilibrium. Living organisms are highly ordered, non-random structures, immensely rich in information and thus entropy poor. This idea ties into the second law of thermodynamics, which states that the tendency in nature is toward ever greater disorder in the universe. So, what can we conclude from all of this? Well, box 1 to 3 helps us understand how entropy plays a crucial role in the behavior of chemical systems and living organisms. It sheds light on the delicate balance between order and disorder, and how living organisms constantly invest energy to maintain a dynamic steady state. If you enjoyed this video, don't forget to watch the second part, give it a thumbs up, share it with your friends, and subscribe for more videos. See you next time.
Pharma Pal.